afternoon, everyone. Welcome to today's public Rothschild lecture. My name is David Hughes. I'm one of the organisers of the 6-month programme on anti-diffusive dynamics, which is running at the moment. So it's a pleasure to introduce today's speaker, Professor Sriram Ramaswamy, who is the Rothschild Distinguished Visiting Fellowship for our programme. So Sriram obtained his PhD in 1983 from the University of Chicago. He was then a postdoc at University of Pennsylvania, and since then he's been at the Indian Institute of Science in Bangalore. So his research interests are very broad. They cover statistical physics, condensed matter physics, soft matter physics, and biological physics. Of particular note, I think, particularly for our program, is that he's one of the pioneers of the field of active matter, systems that can extract energy to drive their motion. Sriram has received many accolades for his work. Of particular note are the Shanti Swara Bhatnagar Prize, the Infosys Prize for Physical Science. He's an elected member of all the Academies of Science in India, and he is a Fellow of the Royal Society. So we greatly look forward to his talk today. Please, Sriram.
Thank you very much, David, for a very kind introduction. And thank you very much for inviting me to give this Rothschild lecture. I feel terribly honored and really thrilled. I'm also terrified because the remit is to give a talk to a mathematically literate, it's not a usual public lecture, we show lots of pretty pictures. I have to talk to a mathematically literate audience, and I'm mathematically semi-literate. So, so it remains to be seen how this goes. And I also notice, too many friends in the audience who heard some of this before, but we lived. Okay, and yeah, that's where I am. I also have an affiliation with ICTS, which I mentioned, and that's primarily who funds me. Okay, so my talk will be outlined this way. I'll tell you about active matter, in particular about active fluids, and I'll tell you about this funny phenomenon in active fluids that has come to be called active turbulence, even though pointy-headed purists might say, look, that's not turbulence, it's something else. So I'll tell you sort of something like our current understanding of it, and then some novelties, a different kind of active turbulence involving the concentration field. And then actually I'll shift gears to something rather different if I have the time, and then I'll summarize. This might be better, right? Yeah. So, as all of you no doubt know, you call an active particle is a thing with some works inside and a power source, which allows it to, from which it takes power and turns it into work. So obviously it's a way of trying to describe living stuff using condensed matter physics, and you can also make artificial realizations, sophisticated ones or ridiculous ones, as you'll see during the talk, or maybe not, yeah. And the basic idea is it's a system made of particles, each of which carries a dissipative arrow of time at the scale of the particle itself. So collections of particles, each particle directly energized. And collections of these are called active matter. And it's a field that's sort of overpopulated by reviews, so much so that some friends of ours have written a review of reviews that came out last week or something. And maybe there he is. So I won't list all the reviews because you can just read that. But, sorry, yeah. I mean, a recent perspective by some of us might interest you in particular. Okay, the kinds, you can have many different kinds of objects that you call active particles because, the particles themselves could just be little round blobs that dither around but in a semi-purposeful way. So you might call that scalar active matter, like these chemically propelled droplets. They might actually be vectorial objects with a head and a tail and going somewhere, like this sardine spool. They could also be other kinds of funny active particles like these, for which I guess I have to go here. And so these are objects which aren't on average trying to go anywhere. They're sort of jittering back and forth, but more along their length than transverse to their length. It's as though their longitudinal and transverse motions had different temperatures, which you will agree is a way of being out of equilibrium. There are many others, but I won't spend time on it. I think more important for the purposes of this talk is the dynamical ensemble or dynamical regime we'll work in. The case we're going to be interested in this talk is not of a collection of objects on a dry terrain, which sort of passively sort of balances the books as regards momentum conservation. Instead, you have objects executing their active processes in an ambient bulk fluid. As a result, momentum conservation is of overwhelming importance, and anything that one of those particles does has literally far-reaching effects through the ambient fluid. So in a completely viscosity-dominated regime that's usually called the hydrodynamic interaction, you can imagine that interaction having a very different shape for fast-moving objects than for slow-moving ones. But anyway, this is the regime we'll work in. And for better or worse, the field has agreed on a terminology which I think some of us invented. We call this dry active matter and that wet active matter. So the subject of active fluids actually is an old one, and even within mainstream fluid mechanics, people worried about active stresses and fluids containing processes which generated internal motions quite a long time ago. In effect, Finlayson and Sriram invented what can be thought of as the active extension of a model which Hohenberg and Halperin in their review called Model H, which some friends of ours, some who must be in this room, invented. But in fact, roughly speaking, it was presaged by the work of these guys, a paper which I recommend reading. And somewhat more recently, the general subject of motile things in a fluid and their dynamics, the dynamics of their concentration and their orientation, their coupling to hydrodynamic velocity is certainly studied a lot right here by people like Tim Pedley. And nonetheless, there's still things to work on. Let me tell you our interest, okay? So, and our approach. So we'll consider a collection of particles with some kind of interaction. It could be steric or something more complicated, which promotes alignment. So there are particles with an axis, maybe a head and a tail, maybe there's an axis. They like to line up with each other. And so if they were just dead Brownian particles, they'd form a liquid crystal at high concentration. The order could be merely uniaxial without a sense of forward and back, or it could be vectorial, where these objects are not only lined up as regards their axes, but all facing the same way. So these are the kinds of systems we'll mostly talk about. And we'll take a very large-scale, coarse-grained approach in which we keep track of the densities of conserved quantities and the order parameters that characterize the ordered phase and the sort of soft fluctuations about those ordered phases, the traditional broken symmetry hydrodynamics. One point I want to make is whenever I talk about a velocity field in this, I'll be talking about the suspension velocity field. I've got particles and fluid. The only momentum that's conserved is the momentum of particles plus fluid. So I'll be talking about the barycentric velocity field of all those guys. Also, I will not distinguish between the mass densities of the suspended particles and the fluid. That would introduce a complication that I don't want to think about today. Okay? So whenever I say velocity field, I'll mean the suspension velocity field. So my picture is not that I've got an object here, it's got no slip on it. I'm taking the particle and the fluid together. And using sort of pure thought, you can build the hydrodynamic equations. You can start with equilibrium liquid crystal hydrodynamics as an origin, and then add in stuff that the spatial symmetries of the system permit, but cannot be derived from the free energy considerations that give you the equilibrium dynamics. You could do this by actually building it from microscopics or invoking general principles and writing them down. So that's how we'll work, the latter mostly. Okay, and we will be talking about ordered states, so we need to understand a little bit about how those kinds of ordered states could come about. And historically, really, people were looking at agents trying to line up with you, trying to stay together and line up with each other. And all of you know this model known as the V-check model, in which primarily as a result of trying to steer towards the average heading of their neighbors, at low noise and high density, you get a flock. You can turn that particle-based theory into a field theory. And the reason I'm going through all this is we need all this to add fluid dynamics to in order to understand wet flocks. So right now I'm trying to describe dry flocks. Okay, and I need a more copy, sorry. So you can describe the orientation of these particles, the vectorial orientation by a field P, their number density by a field C, and you can imagine that in the absence of active processes, they have some interaction that promotes alignment, and let's say a tendency locally to form a polarized state, a tendency for that polarized state to point the same way everywhere, and possibly a symmetry allowed coupling between concentration and orientation of this form. This could happen purely, again, for steric reasons. You know, the particles have a shape, a head, a skinny front end and a fat back end. They might like to point to dense regions or the other way around, depending. Okay, and this, now what makes this system active is that the way they point is also the way they move. What that means is they'll carry themselves and they'll carry their orientation. Not necessarily with the same speed, because the whole thing is also taking place on a substrate. Okay, so in principle, these two can differ. That's not an important part of my story. And this, with noise, is well studied, and many, many things are understood about it. The ordered state is reasonably well understood. The transition is reasonably well understood, and so forth. If there's anything pressing, you can always stop me with a question. Our interest is to ask what happens when you add a fluid, and you know this is our interest for many years. So you need to know how to put active particles in a fluid. And I think probably everybody in this room knows that the minimal way of doing it is to just say that swimming is a force-free process, right? It's not that somebody from outside is dragging you. And so you invent elementary configurations of force which add up to 0. And the simplest are those that pull along their axis and squirt fluid out laterally, or those that push out along their axis and pull fluid in laterally. And you can build the hydrodynamics of active liquid crystals by putting these permanent force dipoles together and building it. Okay, and what you get in the simplest picture where, okay, what do I mean by the simplest picture? Well, okay, so what you'll get from that is something that looks like the dynamics of an orientation field going downhill in a free energy, together with symmetry allowed couplings to flow of three kinds. This contains advection and rotation. This contains the fact that if you've got an elongated object like this and an extensional flow, then the object will line up along the extensional axis. So those are the three bits here. And the physics in here at this level has nothing to do with being active. In particular, I haven't worried at the moment about the fact that P also advects itself. Right now, let's not talk about that. Okay? Any questions? Maybe I should pick on someone. The next part of the story is, so here I've told you what the orientation does to itself and what the velocity field does to the orientation. Here, what the orientation does to the velocity field. These guys carry little force dipoles. As a result, a locally oriented state with orientation P has a local uniaxial stress bilinear in P, plus higher orders in gradients. But at the simplest level, if you've got a swimmer like a collection of swimmers on average oriented like this, they've got a force density that looks like this. Okay, that will give rise to fluid flow, which here we are describing in the strict Stokesian approximation. So stress gives rise to flow, flow affects orientation, and it goes around. Have I said everything? I guess I have, yeah. You can also have what would dominate the physics if it weren't for these active processes, namely whatever orientational elasticity the reference liquid crystalline phase has, and of course pressure. And what you find is, and this is an old picture at this point, what you find is that within this description, in an unbounded system, aligned states are impossible. Okay? These guys go unstable in this mode called splay. These guys, pushers, go unstable in this mode called bend. The important thing to note here is that at this level of description, namely strict Stokesian dynamics, there is a single time scale. The ratio of the intrinsic scale of stress to the viscosity is an inverse time. And everything takes place on that inverse time scale. Okay, so within this weird long-range thing that we're doing called Stokes hydrodynamics, there's at long time length scales, there's a dynamics independent of scale. You can ask, what that means is the line state is unstable. You can ask, okay, these guys are swimming, can they somehow escape this instability? Answer is, at this level of description, no, because the Stokes instability is a single time scale for all lengths, so you can't, it's like Newtonian gravity. It reaches everywhere instantaneously, so you can't outrun it. So merely being motile doesn't help. So I trust that point is, am I laboring the obvious or being obscure? All right. The end result of this tendency to go unstable is that, as I said, you have essentially all perturbations grow with this kind of growth rate. You can assess that growth rate in the following way. You can say that these little swimmers have a thrust F, a stroke L, and are present at concentration C, and that gives you a scale of stress. So then you can say what happens as a function of the length scale at which you're looking at it. At short length scales, relaxation because of crystal elasticity can save you, but that has 2 powers of length in the denominator. This is scale independent. As a result, everything is unstable on scales bigger than this characteristic length scale, which emerges from comparing the elastic constant to the active stress. Okay? And the end result of the instability is active turbulence, which we'll show you the movie. Beautiful movie from Zvonimir Dogic's. These are microtubules driven by molecular motors, which are kept going by a steady supply of ATP, and some tricks to make 2 microtubules come close to each other. So you can see it's a self-stirring fluid. It's got a lot of liquid crystalline order locally, but eventually, on long enough time scale, long enough length scales, it just stirs itself out of existence. And in some sense, in many people's minds, this is the best you can do to get an active crystal. So flux and fluid just, in some way don't exist. And you can ask, okay, if you accept that, what is the effective theory of this kind of self-stirring fluid? So then you can say that, well, it's basically a Stokesian velocity field driven by these stresses coming from the orientations of these guys. Those stresses decorrelate in a time set by this natural time scale in the problem. So it's as though you've got a Stokesian fluid driven by a colored noise with sort of uninteresting spatial correlations. Important, 2 things. There is spatial structure on this scale psi, which is the scale determined by the ratio of elastic constants to active stress. And there is temporal structure and scale small compared to the time it takes this instability to kick in. So you've got a short range correlated, but not delta correlated in time, noise. And as a result of this, if you ask what is the induced correlations in the velocity field, they will all decay in this time scale, but you can do the sums and check that they have a power law decay spatially, as was pointed out by this group. Okay? You'll see later that this picture holds only if you ignore inertia totally, and this power law is cut off with a correlation length set by how far vorticity diffuses during this time tau. But we'll come to that later. Okay? So the active turbulence state on big scales doesn't really contain any information about the fact that the machine, the engine driving it, is a liquid crystal and all this stuff. All that physics is buried below the scale psi and below the time tau. On big scales, you could just have a fluid with a bunch of, anything you like dithering around inside it perpetually. And this self-stirring fluid will be different from a thermal fluid purely because of this. Because what you have is a damping which is local in time and a noise which isn't local in time. Okay? So even if you include unsteadiness and ask for the velocity correlation function, there'll be a range of length scales over which it behaves very different from a thermal fluid. So an actively turbulent fluid actually on big scales is just a sort of disturbed fluid. Okay, on the other hand, The real point of my talk is that we do see stable flocks in fluid. And we know, kind of how they do it. We know that they operate in a regime that is so far away from this viscous regime that, the hydrodynamic interaction, which sort of goes in all directions for slow swimmers, is pretty much reduced to a tiny wake behind the swimmer. So these guys don't see, their interaction is very different. But you can still ask, do you have to be that big and that fast to make a stable flock? Can you be just, slightly big and slightly fast? So, can you outswim that viscous instability? Now, as far as from what I've told you so far, you would think, no way, right? Because that viscous instability is instantaneous Stokesian. Now, let's take a different point of view to understand the hydrodynamic instability of active suspension, active liquid crystals. Let's again take a description in which the fact that the order parameter is polar doesn't enter in. That is, let's take, the technical point. Maybe I should write on the board. When I've got a bunch of things of this sort lining up with each other, and each one, let's say, is some unit vector n alpha, then the object that describes the alignment of these guys when they don't have a head and a tail is the degree to which n differs from the unit tensor, right? And this is the nematic order parameter. So strictly speaking, for headless objects, I should be using this description. What I'm doing here is sort of in between. I'm using a vector, but at the moment I've included nothing that breaks p going to minus p symmetry. Okay? The moment I introduce self-advection here, I'll spoil that. But right now, I'm in a sort of funny, kind of polar, kind of nematic situation. Since the order parameter is polar, but I'm neglecting all p going to minus p breaking terms. Okay? Take this dynamic. So now what do you have? You've got dp over dt couples to flow. You've got d velocity over dt couples to p. If you put these two together, then roughly speaking, dp over dt is, let's say your reference state is where everybody is aligned. Okay? So dp over dt is roughly one derivative on the velocity. du over dt is one derivative on the angle perturbation. Okay? So you will get, in principle, a response which is frequency squared proportional to wave number squared with some complicated direction dependence. It's a little bit like what you get with alpha-in waves or something. You've got a bunch of lines, things under tension. It's complicated by the nature of these beasts. Okay, so what you end up getting is p double dot is wave number squared times p with a prefactor which now is the square over speed. Now we're working with stress and density, not stress and viscosity. So what you get is a velocity scale. And you get omega squared goes as q squared with a velocity squared here, and something which, whether you like it or not, will change sign as you go through zero. So it's that if you've got a bunch of purely nematic swimmers lined up, they won't know which way to go at precisely 45 degrees. This sound speed squared, this active wave speed squared goes to 0 at 45 degrees. So just above 45 or just below 45, depending on which type of stress you have, polar or pusher, you'll go unstable. So this, I think, is a better way of viewing the instability of aligned suspensions. And the reason is that you have a time scale that depends on length scale. What does that mean when it's not a propagating wave? What it means is that on a length scale L, it takes a time of order L for perturbations to grow exponentially by, say, 1 e-fold or something. So it's an invasion speed. How long does it take disturbances on a given big scale to grow appreciably? So now, because we're keeping track of the fact that there is a mass density. Remember, I insist, this is the total mass density. It's not a concentration, it's the physical mass density. So an active fluid with inertia, even if purely pneumatic, has a characteristic speed scale. And now you can ask, can you outrun this speed? So now you can ask, look, we're not just pneumatic particles, we actually know front from back, we swim, and can we escape this instability without swimming it? That is the idea. And this idea implicitly was there really even in our work 20 odd years ago, and we didn't pursue it. So now you can write down the coupled hydrodynamics of a velocity field and a polarization field. And the only difference is I've got this here. I will tell you that for the purposes of the work I'm talking about today, I will not need to worry about u dot grad u because over a reasonable range of scales, the velocity fluctuations are not very big. But in fact, it's not on this slide, yeah. Prasad Perlekar will be talking about this work next week in the conference. I see him. Oh, he's somewhere else, yeah. And he will discuss that issue. So right now, let's say that we're including inertia only at the level of unsteadiness. Okay? You can do better, but today we won't. And so if you put this together, these two together, now again, consider an aligned state, disturb it, and ask what happens. What happens is going to be a competition between this speed and the speed at which the orientation advects itself. Now, notice I'm using a kind of oversimplified description. This system is made of particles, but I'm pretending that the particle number density doesn't enter into it. You could imagine more than one way of doing this. I don't know if there's a really genuinely good experimental system that will realize this. One is you have a one-component active fluid. There's only the overall density, and that's constant. Let's say, everything, your Mach numbers are too small to worry about the overall density. The other is it could be that it's a system in which there are species that transiently come together and become active and then fall apart. So you have a sort of birth and death of activity. So you could imagine contriving situations in which you can do this. John Toner has sanctified this with a name because it involves populations and births and deaths. He calls them Malthusian. But I think it's inappropriate because neither birth nor death enters your description. Okay, anyway, that word is there to stay since John has invented it. So let's ask what will happen now. What happens now, I can really skip these, is, the important thing is the following. As I told you, there are two speeds. One is the speed set by the ratio of active stress to mass density. The other is self-advection. So you get something, resembling a ratio of two stresses, resembling the square of a Reynolds number. You could call it many things. But this is the key dimensionless parameter that governs everything in this problem, right? It tells you whether you can swim faster than the invasion speed. And there are two other parameters which are essentially equal to each other. They have to do with the rate of orientation diffusion to vorticity diffusion. Okay? And in molecular or colloidal systems, these numbers are always very small, order 10 to the minus 4. But you can explore what they do. It's not very clear they do much. Remember, also, we're daringly applying this to very macroscopic systems. All we know is if those systems obey number conservation and momentum conservation, the equations should broadly look like this. But we have no idea if an object we put in there, which is called a stiffness or a viscosity, really has values that are anything like the molecular one. Okay, because you could have, on the scale of a small fish school, you could have an effective eddy viscosity, which is much bigger, right? So all I know is on symmetry grounds, my equations are okay. I won't stake my life on numerical values. That's also important to keep in mind. The other thing is, for things like the aligning interaction, you don't even know if they're mechanical. They could actually be behavioral, in which case, even more, you don't really know what their values are. If these guys can see fairly far ahead, maybe the effective stiffness is hugely enhanced. So frankly, I don't understand the numbers in this problem, and maybe that's a topic that should be taken up more seriously. All right. So as I said, it's going to be a competition between the invasion speed and self-advection speed. And so what you find if you do a small wave number analysis for this non-dimensional parameter in a region of order unity, but maybe a little bigger, is you get this wave speed term with this combination, V0 squared minus sigma a over rho, square root. Therefore, clearly V0 squared is small, this is imaginary, and this is a growing mode, linear in wave number. If you work to next order in wave number, what you see is there's another term, which the moment you cross, you're safely out of the domain of this instability. What that gives you here is a mode at order q squared, which is now a growing mode. Earlier it was some uninteresting modification to wave speed. Once this becomes real, this becomes a growing mode. So as you increase this quantity, you go, let's say, imagine this quantity was 0. Then you have the Stokesian instability, that's a red curve, growth rate non-zero at 0 wave number. Crank up the swim speed a little bit, you now have this linear and wave number instability, which I've zoomed and shown you here. That's this dashed line zoomed shown here. Increase slightly more, you now get the linear instability is gone, but you still have a growth rate quadratic in wave number. If the speeds are large enough, the system is 100% linearly stable at all wave numbers. So already what this tells you is the linear instability of flux in fluid is something which you can get rid of by swimming not very fast, moderately fast, okay, compared to the growth speed. Okay, so that's, by the way, and here is one of my excuses for giving this talk in an anti-diffusion conference. This is anti-diffusion. It's a growth rate quadratic in wave number of velocity gradients, okay? All right, and so what you get, this is work done with these people, Ryan, Aditi, Navdeep, who's now a postdoc at Göttingen, and Prasad, who is around but not today. He'll be here next week. You get a dynamical phase diagram. If you take that linear stability phase diagram, this is the region where things are unstable with growth rate linear in wave number. This is the region where you have order q squared growth, and this is a region where everything is linearly stable. If you study the full equations numerically, with or without the advective nonlinearity, you find a ferociously turbulent, defect turbulent state here. You find something that's, of course, dead stable there. In between, you find a state where there are sort of growing modes, but it turns out it manages to survive and remain ordered. Okay. You can read about this in a paper that's now a bit old. We've done more on it more recently, which I'll tell you about in the next few minutes. Okay. What do these states look like? Visually, they look like this. They look like defect turbulence. Notice it's a vector order parameter. The topological defects are therefore integer strength. They're hedgehogs or whatever they're asters and anti-asters, or vortices. And as you increase this motility parameter, you go to a stable state. What's fun to see is what these two noisy states look like. Here is defect turbulence, thanks to Navdeep's movie. Purnima's nice movie. So you can see two things here. You can see that you get asters or hedgehog defects. You can also see that the compensating anti-aster sort of gets stretched along. This is something that happens because of the self-advection. If, on the other hand, you're in this region where growth rates are quadratic in wave number, you get perturbations that seem to grow but eventually somehow right themselves. And frankly, I personally don't understand in any detail why this can happen. Short, wasn't it? But the point basically is that somehow it seems to be a case of a situation where the growth rate is small enough that as it grows, the amplitude gets big enough that nonlinearities get important, and somehow the weight is transferred to those larger wave numbers and it goes away. So as far as we can tell, there really are two distinct dynamical states here. And this one, phase turbulence, you can call it, is an on average ordered state. Okay, and you can measure the properties of this transition. You can measure the magnitude of the order parameter as a function of R, and there seems to be a reasonably clean onset. You can measure correlation functions, and as you approach that threshold value of R, they start to decay more and more slowly with a reasonably nice data collapse. And we can demonstrate a kind of modest growth of the correlation length. This is 1 upon the correlation length plotted against 1 upon that inertia parameter. And extrapolated, it seems to go to 0, that is, size seems to go to infinity at an order 1 value of this parameter. Okay. And this is all reported a few years ago. As I will say more than once during this talk, I don't really know the kind of experimental system in which this can be tested, but it would be nice to have it. So that is the story of this part. There's, okay, I guess one of the interesting features is if you work in the mildly unstable region, the phase turbulent region, and you look at the average order parameter and look at fluctuations. So let's say the order parameter is pointing this way. Look at the transverse fluctuations, that is the broken symmetry mode. If it's a genuine ordered state, those should have a weight, the variance of those should have a weight that grows, let us say, roughly speaking, 1 over wave number squared, as happens for the normal Goldstone modes in any broken continuous symmetry state. And if you look at the transverse versus the longitudinal fluctuations in that state, you can see the transverse ones are substantially bigger. So let's see it here roughly. So there's some sign that you're actually seeing the broken symmetry mode. The other fun thing is to ask, remember I mentioned that it scales bigger than I told you two things, there are two lengths. I told you there's a scale below which elasticity is important, above which active turbulence dominates. And I also told you another scale, which is how long vorticity diffuses in the correlation time of the active process. And I argued that between these two scales, the velocity correlation should have a 1 over wave number squared behavior, and then on big scales they should flatten out. This is the energy spectrum, which is q to the d minus 1 times the velocity correlator in 2 dimensions, so it's q over that. And it fits roughly a q over constant plus q squared. It's not squared, it seems to be about 2.3, reasonably nicely. So this picture that an active fluid on scales above where you can resolve the crystalline details is sort of a generically stirred fluid, is borne out by these measurements. And what's worth. Okay. Now you can, so far as I said, I've avoided discussing the particle concentration. You can, by just pretending it's not there. The other thing you can do is you can say, imagine the system is so concentrated that the particle phase velocity field itself is divergence free, right? So the polar orientation of the particles is a surrogate for their velocity. So you can imagine working in a dynamics which constrains the polarization field also to be solenoidal. Some of the features I discussed just now, a linear in wave number and a quadratic in wave number growth rate regime exist, but the magic that led to a noisy but ordered state in the general case somehow doesn't survive here. Both of these are defects turbulent, and then up here, of course, things are completely linearly stable. The defect structures themselves, clearly because P is solenoidal, the defects will all be these vortex-type defects, not radial, not asters, right? Because they're divergence free. And see what the dynamics looks like. So the instability, you see this bend instability kicking in, and then gradually these vortices forming. We haven't analyzed this in any serious quantitative way to say much more about it. Okay. And there's no evidence for the correlation length diverging at a finite value of that inertia parameter. It looks like you have to sort of go all the way to infinity before you see it diverging. All the way to the linearly stable regime before you see it diverging. One sort of curious feature is that the vortex cores, as you go from the low R to the high R region, go from being more or less homogeneous and isotropically distributed to forming string-like structures. You kind of see that in the spatial structure of the orientation field also. So there's some degree of reorganization, fairly well defined in the sense that the radial distribution function of the defects viewed as a liquid goes from looking like R squared at short distances to linear in R as you increase the inertia parameter.
What is the size of the particles?
There are no particles in this. This is only a, so the entire numerical study is a polarization field and a hydrodynamic velocity field only. So the short distance cutoff is set by the short distance cutoff, the largest wave number of your pseudospectral study. There are intrinsic length scales in the problem that tell you the effective size of the degrees of freedom in this problem is clearly the size below which the detailed physics of the crystalline alignment matters and above which it doesn't. On scales bigger than that, it's a bunch of sort of driven particles moving around with no particular correlation. So that's about all. Yeah, and this you can read about in this paper. So there's, I have enough time. There's a lot of sort of theoretical challenges here. One is, I told you about this phase turbulence state. Now, in various pieces of work, but probably most well-known, Jayaprakash Iyer and Pandit 30 plus years ago, they showed that the Konomoto-Sierczynski equation, which has a band of wave numbers over which the growth rate, it goes up quadratically and then comes down. So it's like this. So this is growth rate against wave number. Can people see this reasonably? Okay, yeah. So you can ask, you can say, look, let me treat all of this side as small length scales. And supposing I want an effective theory at the large length scales, the small wave numbers, by solving for these degrees of freedom in terms of these. And imagine doing that actually numerically. Okay? Then you could ask, does the fact that the dynamics is spatiotemporally chaotic mean that the effective description on large scales is that of a stochastic PDE? Does the fact that there's a negative diffusivity for the uncoarse-grained theory translate instead into a positive diffusivity and a noise? And Jayaprakash Iyer and Pandit showed that this was the case for KS. It would be wonderful to do something like this for this problem, but I think it's technically far more difficult. So that's one of my dreams or nightmares for this problem. The other, many people, Toner and others, have worked out the theory, the sort of full normalization group theory with various limitations of dry flux. If you do the sums, you will find that when you include the hydrodynamic velocity field, and now that you're assured that the fatal instabilities in the Stokesian regime are cured once you have inertia, you can ask, if you have a flock in fluid with inertia, what is the asymptotic behavior of the correlation functions there in the ordered phase? So take the PDEs I wrote down with nonlinearities and with noise, and do you have the mathematical theoretical muscle to do a normalization group theory of that and calculate everything? What I know is the velocity fluctuations are precisely as relevant as the polarization fluctuations. So you have double your money, double your fun.
And this normalization theory yields dependence of the transport coefficient.
Yeah, so you will get the
scale.
That's exactly. So it's like what you do for critical dynamics, or in principle for certain kinds of turbulence. But here at least you don't have forcing entry from large scales. It's driven on. I'm saying that you don't have to introduce very pathological noises. It's not like what some people have done for fluid turbulence. In that sense, it's not as odd as that. So this is another challenge, and I think maybe apart from all this, the point is, if any of this stuff is to be used, somebody needs to come up with a system where you can tune, where let's say the swimmers have Reynolds of order 1 on that scale, and where you can somehow tune speeds. Maybe the way to do it finally is to do a particle plus fluid simulation and see if these phenomena reproduce themselves. I don't know. Okay, so I want to spend a few minutes now. So far I've told you about flocks in fluid, but the flocks had a presence only in the form of their polarization field. Their concentration entered nowhere. In one case I said it's an empty fluid, no concentration, and then I said it's a fully packed fluid, so dense that the polarization is solenoidal. What if I want to look at the dynamics of the concentration field? So then I have to go back and study those, and that's part of Purnima's PhD work. Purnima is a student of Prasad's. You can read about it here. You can listen to Prasad's talk. I've spelled his name wrong, my God. Sorry. Anyway, so basically what happens to this picture when you introduce the concentration field? Well, so now first let's go back to a dry flock. Let's forget about the fluid flow. Let's keep only the polarization and the concentration. So then what you have is the polarization, the dynamics, You can take a simple-minded picture with the polarization and the concentration coupled in the free energy. This will give you a term proportional to grad C in the polarization equation. And the fact that the concentration is carried by the polarization will give you this. So these two together means that the dynamics at leading order in wave numbers is wave-like. And now, what happens when you include the fact that there's an ambient momentum-conserving fluid as well? Okay. So let's take advantage of what we've learned from fluid flux with inertia to say that we'll work in a regime where the instability that led to the active turbulence that we've spent the first 40 minutes of this lecture discussing has been eliminated by working at large values of that inertia parameter. So your self-propulsion speed or your self-advection speed is big enough that you don't have the active instability. But you have now the coupled dynamics of the concentration, the orientation, and the hydrodynamic velocity field. And what happens? The question. Okay. Well, so you can write down basically the difference will be the following. The fact that even at the level of a free energy functional, the polarization and the concentration coupled this way will mean that you will get stresses from concentration fluctuations driving fluid flow. So a local concentration fluctuation will do two things. It will reorient the orientation and it will drive fluid flow. So when it reorients the orientation which is the velocity of the particles relative to the fluid, roughly speaking, will respond. These two guys together, if it weren't for the hydrodynamic velocity field, gave you those waves that Toner and Tu talk about. So now you have two competing responses to concentration or orientation variation. Okay, and if you study the problem, you can again consider an aligned state. Strangely, what you find is you get the waves that I talked about, which would have arisen even if there wasn't fluid flow, and then you get a damping with a piece that can destabilize. More than that, if you actually look closely at the values, it's a bit of a mess here, I'm sorry, okay? But this parameter gamma is a kinetic coefficient for orientation relaxation. So it's roughly 1 upon a viscosity. So the magnitude of this term is actually like the inverse of 1 upon a viscosity, it will be a viscosity divided by density, meaning its magnitude is of order the kinematic viscosity. It's competing with things that are much smaller, the particle diffusivity and the orientational diffusivity. So in fact, generically, you expect this guy to be much larger than these. Okay? So you have one more anti-diffusive instability coming from a source which I don't have a great deal of intuition for, but what it says is that as a function of parameters, you should get an instability in which these Toner 2 type waves grow. So does that happen? So basically, as I said, there's two responses. If you change the orientation, you have a direct response, or if you change the constant, you have a direct response from the orientation and indirect response via the hydrodynamic velocity. And what can happen is that the orientation and concentration, let's say the orientation is relaxing, you sort of get a second kick from the fluid flow. This is a very sort of childish explanation. It's certainly not a mathematically literate explanation, but it's the best I can do. And the other important thing to note is that the polarity is important. It has to be head-tail asymmetric. Inertia is important. You have to have a density, otherwise you don't get this underdamped mode. And and activity is important because the whole effect doesn't arise unless you have these waves whose speed is governed by one of the self-advection coefficients. And you can see what the instability looks like. Purnima's movies. You can watch the dynamics and see that the velocity and the concentration are not exactly in phase. You can study the regime where the system is unstable to growing to concentration waves. So the system spontaneously makes concentration waves, but in this regime, it's probably just a coherently oscillating state. As you increase, basically this coupling between orientation and concentration in the free energy this parameter is the important parameter. And you then enter a regime where you start to cross over to something somewhat more noisy. You can see the order parameter streamlines are pointing this way, and these, the color code is the concentration. To something more turbulent looking of this sort. Rather short. So. Okay, there's a bunch of turbulence physics in this, which Prasad will talk about next week. So I've actually left myself a couple of minutes to tell you about something completely different. Yeah.
Sorry.
Yes, sure.
You said that there are two kinds of diffusion.
Yeah.
One is just particle diffusion, one is orientation diffusion.
Right.
What does it mean, the second type?
So, okay, so supposing you have a, let's forget all this active matter physics. Supposing you have a liquid crystal, a pneumatic liquid crystal, in the ordered phase. Then if you, and for simplicity, let's say it's an ordered phase, forget about momentum conservation. Suppose you've got a pneumatic liquid crystal between two plates, you know, a display screen in an aeroplane or something. Then you know the dynamics of that is a balance between dissipative torques and elastic torques, right? So rotational friction times rate of change of angle is elasticity times two derivatives on angle. And that's what I mean by orientation. Just direct relaxation in an aligned state. Okay, so now I'm going away from active liquid crystals to a completely different problem, still about the concentration field in an active system. This is work that we did with Thibaut de Piré and Yariv Kafri, which you can read about there. The background is that Yariv and friends had studied the problem of an object, an inclusion, in a medium containing active particles. The work they had done was a so-called dry description, where these active particles were active Brownian particles, and they have an interaction with this inclusion described by some potential. Each active particle has a speed v0 and moves in a direction ui. So right now, supposing it's not momentum-conserving fluid, then the particle has this kind of dynamics, self-propulsion and interaction with the potential, and no inertia. The effective dynamics of the collective density of these particles at large length scales acquires a diffusivity given by the speed times the persistence length, and interaction with the potential, and stuff involving all the near field here. If you take an object like this and then ask, this is what I meant to say, reactive particles, yeah, and ask what happens to the density field at long times around such an obstacle, in general, if you get a power law decay of the number density of particles away from this object with a coefficient that depends, that in effect is the mean force exerted by the inclusion on the active particles. As with any mean force, it should be zero at thermal equilibrium. So because this system is out of equilibrium, this thing is non-zero and you get this slow decay. So the question that we, I guess, that Yariv and Thibaut posed is what happens to all of this when the ambient medium is an active suspension with fluid flow in it. Okay? This already has very dramatic effects. You get long-range interactions between passive inclusions, and you can get disorder at a boundary affecting physics in the bulk, and many interesting things. So we just took up the question of what happens if there's an ambient fluid. In that case, the equation for the concentration will be what we had earlier, together with advection by the hydrodynamic velocity field of the ambient medium, right? So this is the only new ingredient. The case of greatest interest is where this inclusion has a vectorial asymmetry. If you take an active medium and you stick into it an object which has a vectorial, front-back symmetric, asymmetric shape, it will start running away. It will self-propel. If you want it not to, you have to hold it in place. That means you have to create a force monopole. If you create a force monopole there, it will generate a far-field fluid flow that goes as 1 over r. So the velocity field, due to an inclusion held by main force at one place in an active fluid will decay as 1 over r. So then what you'll have is this equation with a 1 over r decaying velocity field. So basically, if the inclusion is apolar or some higher, is nearly symmetric, you will get, you can just rescale this problem. You can compare these two terms, and what you find is for the case of a polar inclusion, the decay of the velocity field is 1 over r, and these two terms therefore scale the same way under rescaling, and so this term is marginal. For the apolar inclusion, this term is irrelevant. So you can basically, for an apolar inclusion, you will get the density decay the same as you got in the dry case. For the polar case, something interesting happens. And the interesting thing that happens is that then you have to solve this problem. Excuse me. Solve this problem. And on general dimensional grounds, that density will be a 1 over r squared times a function of L over R, where L is some inner microscopic length scale associated with the inclusion. Okay, that's all the dimensional analysis can tell you. You can hope that this term doesn't matter. If you don't allow for it, what you find is that when you try to solve this problem, then the coefficient blows up at some angles. So your best hope is to actually retain this piece and solve for the density decay, which Thibault did. So this is classic anomalous dimension, right? That your dimensional analysis requires a small scale length which you would normally ignore. Okay, and Thibault did this amazing perturbative calculation where he calculated the decay perturbatively in basically a Peclet number associated with the strength of the active forcing and diffusion. And we get an interesting set of decays for this guy. The decay power depends on the order of circular harmonic, of the M, what's it called? E to the IM phi, that M, okay, which you can calculate perturbatively. And what you find, excuse me, is that I had a slide explaining this in more detail. Drat. Yeah. Anyway, so you find an anomalous decay. So it's really interesting. What it says is the far field decay due to this object knows in detail about the shape of the object in this continuously non-universal form. That is to say, it's not just that polar gives one number and apolar gives another number. The strength of the obstacle is encoded in the exponent of the far field decay. It's almost like you can actually, you're a little critter swimming in this fluid and you can tell details of the shape of the object through the ambient fluid. We're not sure what to do with this, but at the moment all we've done is posted it and sent it to a journal. But so something rather interesting is happening here. The axisymmetric case has a faster decay, and the non-axisymmetric case has a slower decay than in the dry case, which is rather interesting. So the physics of marginal operators and so forth surfaces here in a most interesting way. And so, well, that's my overall summary. I told you a bunch of stories, 3 of which were related to each other and 1 was not. You can read about those here. And I'm just reiterating some of what I said already, the need for controlled experiments, the need for an effective stochastic theory of the phase turbulent state, a complete statistical field theory of fluid flux, and, returning to the topic of this program, can one get structuration, I don't know, staircases or stripes or bands or whatever it is, generated by active turbulence in some of these systems? Can one study it in the presence of a macroscopic gradient and look for these things? These are ideas I've only begun to think about. A related, but actually not completely related idea is when you have active particles in ordinary turbulence. Active particles in ordinary turbulence self-concentrate quite strongly to the extent that they actually form caustics, which you can read about in this work. And with that, I'll stop. I'm only 1 minute over time, but I hope I'm given time for questions. Thank you.
Thank you very much, Sriram. Questions?
So I had a number of questions, but let me ask the most general one first. It just come to the question. Your talk struck me, since I've been conditioned since I first learned about fluids, that all the interesting things have to do with vorticity. And you barely mentioned the word vorticity. I'm wondering if you could, I had some specific comments, but if you could, in more general terms, address things like the vorticity evolution and freezing in and all in the context of these active fluids.
Yeah, so it's not something that I have done, but people, I guess, people studying active turbulence in more detail have looked. I don't have a, I don't have a sort of clean answer that this is what vorticity does. We have tended to look at, to the extent that we look at velocity flux, we've tended just to look at the spectrum rather than vorticity. People have looked at fluxes, cascades, all that stuff. I have not actually involved myself in that.
I'm just curious,
So,
does anyone know what's frozen into what, for example? The way we know that vorticity is frozen into fluid flow.
Right.
Maybe vorticity results in clustering or not?
That's a separate question. Supposing you just had conventional turbulence, supposing you had a vortical flow, and you put a bunch of self-propelled particles into it, then that work explains how, even without inertia, those particles end up clustering because they move persistently. So their persistent motion gives them a kind of inertia, which makes them cluster. Those kinds of phenomena are now beginning, and we're not the only ones by any means who studied this. There's been a fair amount on this. That happens, but that, in a sense, is only saying that self-propulsion is a bit, self-propulsion without inertia is a bit like particles having a mass. And so you can imitate some of those phenomena.
The question has more to do with these polar things.
Right. Yeah, so I mean, the point is there's two kinds of topological things happening here. Because you've got orientational order, you've got the topological defects of that orientational order. And those two very important things. What hydrodynamic vorticity does, I don't know, but it's actually related to the question about whether active turbulence can do the kinds of things that ordinary turbulence can do. So it's in
That's
there.
why I asked.
Yeah, absolutely. And I think, yeah.
Okay, and clustering effects. You said that they're not related with the inertia?
No, the point is, supposing you have self-propelled particles with an inertia-less dynamics. Velocity equals mobility times force, or velocity relative to fluid equals mobility times force. Suppose you just have that, plus self-propulsion. So, I mean, I can just open another talk if you like. So, suppose you've got particles with positions. Suppose you have a particle. So, you've got a particle like this. It's got a position R. It's got an orientation N. There may be some external force field or a force field with which it interacts with other particles. That's this. That's a mobility. And it's in a fluid. And so, in a sort of Galilean invariant description of its dynamics in that fluid is velocity relative to fluid is mobility times force plus self-propulsion. You can then ask, given some form of this, and then I should tell you what N does. And let's say N is, I'm just taking a two-dimensional picture, and supposing theta is just doing rotational Brownian motion. Okay, this is a completely specified problem for a given velocity field here. You can ask, you can show that these guys behave surprisingly similarly. See, the point is this: because this thing is doing rotational Brownian motion, it has a fairly persistent velocity, right? Because it's got a scale of speed, and it's pointing like this, so it doesn't lose its way very easily. So it has something resembling, it's not inertia, not mechanical inertia, but it does some of the same things. And you can study, that problem has been studied by various people to some extent, including us. Yeah, so the answer to that question is those things, it's sort of known. And it's elementary manipulations, and this will show you some of that. Yeah.
And the second question, in view of turbulent transport coefficients, what kind of turbulent transport coefficients in the description there are there? I mean, for example, scale-dependent turbulent diffusion. Yeah, what else? Do you have effective velocity as a transport coefficients?
So what you're asking for is if I have an actively turbulent fluid,
Yes.
you can calculate the, let me think. There's two things that happen. One is that, okay, in general, when you think of turbulent transport, if you've got a fluid with active swimmers in it, the effective viscosity on large scales, even if these guys are just sort of tumbling around, is modified by their presence, not merely because of their concentration, but because of the persistence of their motion. So you get this kind of trivial modification of viscosity by an amount given by the related to the active the force dipole strengths carried by these particles. If you're in the turbulent state, I guess what you have to ask is, if I've got an active turbulent state and I put on a flow, by how much will the stress alter? This, I'm just trying to think. So, do you know if this has been calculated, Christina? I don't remember if this has been done. Yeah. In the actively turbulent regime, I don't know if the macroscopic viscosity of the turbulent thing has been.
As you said, that we look like sort of
Kind of an uninteresting, not highly correlated.
in a flow regime, and then it's not a situation which
Yeah,
is in transport supplies.
Right. I mean, in other words, if you have just a bunch of uncorrelated swimmers, their contribution to the viscosity is easy to calculate. The coefficient of the first order in volume fraction piece depends on the ratio of their, meaning it will depend on their persistence time. Yeah, that you can do. Mike, if I can ask you a question, did you guys in your when you studied sort of turbulent states, did you ever calculate effective macroscopic viscosities numerically? You didn't do that. I haven't seen it anywhere. Yes?
You often used, in your talk, you often used the word experiment. Now, I got the impression that that was mainly referring to computational simulations and whatnot. Is that right?
I would really like it if people actually had, little.
I mean, there are
Really?
at the. I'm thinking of active turbulence that people observe, calling it active turbulence, the bacterial suspensions, of which there are a number of examples in the literature.
Sure.
And it would be possible. It is possible to measure length scales and all the rest. Well, I don't know about all the rest of it, but many other things in those experiments. And I wondered how closely the theories can be refined in order to actually agree with the experiment.
So I thought one wasn't in the purely Stokesian regime. I thought we were in reasonable shape. What I was hoping for is experiments where Reynolds is of order 1 at the particle scale, and even more greedily, where you can tune their swim speed. So these I don't, I mean, that is what when I said experiment, and that's why I said, well, maybe it should be done by particle scale, particle plus fluid simulation, which actually, in effect, is an experiment, because you put it in as particles with some specified surface properties and you see what happens. I'd be happy even with that. But experiments themselves would be wonderful.
Bioconvection theories, I agree, that's pretty different because it's in the gravitational.
Right.
that leads to length scales come out of it, and I've temporarily forgotten the next point I was going to make, as happens occasionally.
To all of us.
Yeah, you'll have to, I'll
Yeah.
remember it.
Gotcha.
after.
Sure. Over wine.
Yeah.
We know that it does.
Now, in your model where you have the concentration and the polarization,
Yeah.
what is the relation between the two? I mean, because the polarization is the spinning direction of the...
Yeah, so the continuity equation, so I must, maybe I went faster, too fast.
So to find this the question, so that means if the concentration is very low, I mean, then
Yeah.
P should somehow vanish as well.
Yeah, so if you have, depending on how far, clearly the concentration dependence of everything is hugely important in this problem, right? So absolutely, that will matter. So if you're in a regime where concentration fluctuations are enormous, you really have to worry about that. Yes.
But is it in the model?
At the level of analysis that we have done, it doesn't really enter into it because for the most part we've done linear analysis. We do have the density dependence of the, we do have the concentration dependence of the sort of, okay, I haven't written it that, sorry, this, excuse me, this is misleading in the sense that I should have, where should I go? Yeah, I guess I can go here, yeah. So, I've written this as though, I've written this in this form, but actually what we have is a quadratic and a quartic term, and the quadratic term has a concentration dependence. So that's there. Numerically, it's easy to do. At that level, you can put in your favorite concentration dependence. So at low concentrations, it will not want to order at high concentrations. That is very much in the problem. We haven't, what I reported to you today didn't really rely very much on it. But yes, it's there. Yes.
I don't know if I understand your part very well. Could you go to the instability, the dispersion relation?
The instability?
The anti-diffusion, for the
Yeah,
instability.
okay. You want the dispersion relation?
Yeah.
Yeah, hang on.
Yeah.
Yeah.
Not this one. Oh, yeah.
Okay, maybe this is too messy. Maybe it's a purely pneumatic case.
Yeah, you have an anti-diffusion term.
Yeah, it was there. But there's more than one. So which one do you? Did you? What?
Show it a few minutes ago.
Hang on. Is the anti-diffusion one involving the concentration or not?
Yeah.
Ah, okay. Then it's after this. Excuse me. It's down here.
Oh, yeah, this one.
Yeah.
My question is,
Yeah.
this gave a threshold for the instability, right?
Right.
So if the threshold cannot be satisfied,
Then it's not unstable.
yes. If we don't have instability, do we have still have a concentration through the wave coupling?
Yeah, that concentration coupling is there. The difference is that if you're in a regime where this instability is kicked in, the system will spontaneously make those concentration waves. If you're where it's stable, if you perturb the system, the concentration and polarization response will be wave-like. But there will be no spontaneous fluctuations. That's the difference.
Could I just ask one general question? So if you wanted to model a flock of birds, are there global studies as to what shape of flock is stable, what concentration is stable?
Yeah, so I'd hesitate to do flocks of birds with this kind of treatment for multiple reasons. One is I think they look fairly far around them. Two, actually, one general point. Okay, so multiple points. One, I'd be, just given that what we've done here is to go a little bit away from the purely viscous limit and say, you had this almost isotropic and infinitely large boundary layer, and now I'm swimming a little fast, so it's a little bit combed back. That's the regime we've worked in so far. In the case of birds, clearly that's not what's happening. It's clear that the birds must sense each other hydrodynamically also, not only visually, I would think, but I don't know about the extent to which that matters. I would say the short answer to your question is, even though birds are a wet active system, in the sense that they're an ambient, I don't know about the extent to which the wet matters. Partly, as you said, these things tend to be finite, which means they're somehow intrinsically in a biphasic state where you've got a lot of concentration in some places and none elsewhere.
I think you'd be better off thinking about sardines than birds.
Yeah, but he asked about birds. Yeah, I'd be happier. Yeah.
Sardines is fine
You
as
can
well.
eat both. But yeah, so I mean, I don't know what to do when the interaction is so very non-viscous.
Presumably the sardine boundary layer is quite sticky.
Right. But I'm saying that in a sense, the sardine boundary layer, here's my sort of non-fluid dynamic point of view. I've got a collection of sardines, I've got a bunch of fluid. I'm still allowed to write down equations like this. If I just smooth over the sardines, it's a momentum conserving system. There's neglecting death and fishing and birth and so forth. There's a conserved number of sardines, a conserved total momentum of sardines plus c. So I'm entitled to write down equations like this, meaning there's some noise in the system. A smooth gradient expanded description should be okay. I don't know what value I'd give to the quantity in there that I'm calling a viscosity. I think that's the right statement. It's modified both by the concentration of the sardines and by the fluctuating, the sort of something like turbulence or whatever is taking place on those scales. But I would still think on a scale of 10 sardines, I can do a gradient expansion. And I'll put in a coefficient there, but I don't know how to do viscometry on sardine schools. But maybe one should.
Right. On that note, okay, minute will thank Sriram again. I should just say there's a drinks reception outside, so please stay if you can. And let's thank Sriram again for wonderful talk.